In this section, we're taking a look at hypergeometric distributions. So what we're looking at in this case is just looking for successes and failures in our dependent trials. A random variable in this case is going to be the successes in a given number of trials. So how frequently are our successes? The probability of any given trial being successful would be given by the equation A choose X times N minus A choose R minus X over N choose R, which sounds really complicated, but in general, it's just how many ways can we get what we want on the top divided by how many ways we can make it up in total. We've done this before with our combinations unit, so this isn't really something new. And just adding on now our expected value being the number of dependent trials times the successful outcomes in the population divided by the population size. So we take a look at this in an example. It might make it a little clearer. If we have a team selected from 6 women and 9 men, we want to make a team of 4, and so we're getting 2 men and 2 women and we want to find that probability. So we've got 2 women and 2 men. And now if we're going to make a team, we got to select our women. So how many ways can you make a team of 6 women, of 2 men and 2 women? So 6 choose 2. 6 women choose 2 of them to be on the team. And then multiply that by 9 choose 2. 9 men choose 2 of them to be on the team. And then divide that by the total number of ways of choosing the team. So there's 15 people, choose 4 of them. So again, just like in our combinations section, we have that working out to about 39.6% or 0.39. So there's about a 39.6 or 40% chance of 2 men, 2 women being selected. And so that, again, is just the workout of that formula that might look confusing there, but in general, we've used this before. Moving on to some distributions now. So we're going to have a bag of jelly beans containing 10 jelly beans, 4 blue and 6 green. If 4 jelly beans are selected at random, we want to create a probability distribution for the number of green jelly beans selected. So in 4 pulls, we can draw 0 jelly beans. We could draw 1 jelly bean. We could draw 2 jelly beans, 3 jelly beans, or we could have 4 jelly beans selected. So that's what we can pull out. And we need to do our probabilities. So our probabilities in each case is going to be 6 green jelly beans, choose 0 of them, times 4, choose 4 of the blue jelly beans. So 6 choose 0 times 4 choose 4, and then we're going to divide that by the total number, which is 10 jelly beans total, choose 4. So 6 choose 0 times 4 choose 4 over 10 choose 4. That's going to give us our probability. Picking green, picking blues, and then out of the total, that gives us 0.00476 as our probability. We're going to do the same thing all the way down. 6 choose 1 times 4 choose 3 over 10 choose 4. 6 choose 2 times 4 choose 2 over 10 choose 4. 6 choose 6 choose 3. Select 3 green jelly beans times 4 choose the 1 blue jelly bean over 10 choose 4. And finally, 6 choose all 4 of the jelly beans being green times 4 choose 0 having no blues over the 10 choose 4 the total ways. So we'll calculate each of these out, and they work out to 0.11426, 0.42857, 0.38095, and 0.07 0.142. And now, just because we're going to end up calculating the expected value, we'll multiply these now while they're in the table here. So if we multiply these out, we get 0, we get 0.11426, we get 0.85714, 1.14285, and 0.28572. So that's just our multiplication there to get ready for our expectation that we're going to do later on, and we'll show that this sum here, and actually to sum it up now, the sum of that should work out to approximately 2.4, and so this sum here should work out to the formula that we looked at earlier when we calculate it in a later question. If we're going to illustrate this distribution in a histogram, then I've preset that there, our 0, 1, 2, 3, 4. There is no 5 jelly beans, but we can put our different columns in there. So our 2 jelly beans is going to be the peak here at 42.8. So that's going to be about, let's say here. This is just a rough sketch of this. And then we have 38%, so somewhere around here. And then we have 4 at 0.07, so that's going to be about 8 here-ish. 1 is at 11%, so it's going to just be slightly above the 0.1, and then 0 jelly beans is at less than 1%, so it's just going to be really low here, maybe just like almost a line just to show that it's there. So we have our 0, we have our 1 here, we have our 2, we have our 3, and we have our 4 jelly bean selection. There is no 5th selection at all, so we can scratch that one off. So there's our distribution, and we see that it's somewhat of a bell type shape, slightly skewed over to the left side. So there's a little more weight on picking 1 or 2, a little more weight to that side, to the 1, 2 side than there is to the 3, 4 side. But if we compare that to our sum again here, which is our expected value is 2.4, and so 2.4 is somewhere in between here, and that looks pretty accurate, right? We got more 2s than 3s, so it's used a little to the 2 side, but 2 and 3 are very popular. Moving on. What does our P0 tell you is the next question. So if we look back at that, probability of 0 is 0.00476, so less than 0.5%. What's it tell you? At less than 0.5%, it means you're unlikely to pick none. You're going to probably pick a green. And then our expected value, so we calculated that earlier as 2.4. If we use the formula there, so the expected value of getting a green jelly bean is the total what comes first? Yeah, the total number of the dependent trials. So we're doing 4 trials. So that's our R value times the successful outcomes, which is 6 possibilities of pulling green, right? Divided by the total number of outcomes, which is 10. And so when we multiply that out, we get 24 divided by 10, or 2.4. Do note that there's 6 out of 10 green, and we're multiplying that by the 4 times. So if there's a 60% chance of pulling a green in general, and we're pulling 4 times. So 60% of 4 is 2.4. So there's our expected value in another, reading it a different way. If we move on, let's take a look at one of those cases where the probability is at least a certain number. So here we're going to have at least 3 males. If you recall, doing these types of combinations, we can either do it directly or indirectly, whichever way is going to be easiest to do with the fewest calculations is usually the best. Both ways will work. So here we have 24 students have signed up to attend a workshop, 14 females and 10 males. 7 are chosen randomly to attend. What's the probability that at least 3 are male? So that means we could have 3, 4, 5, 6, or 7 males. Conversely, we could have 0, 1, or 2 males attending, and then subtract that from the total number of possibilities or combinations to determine that. So the total number of combinations, that would give us fewer calculations in general. And so we can do that one up here with our probability of 3 males being equal to 1 minus, so the total probability minus the probability of selecting 0, 1, or 2, 3, 1, 0, 1, or 2 males. So selecting 1 male, or sorry, 2 males is going to be 10, choose 2, times 14, choose 5. And that is picking 5 females and 2 males. And then we're going to, I'm going to do this as one big probability, so I'm going to add these up. 10, choose 1 male, times 14, choose 6 females, plus 10, choose 0 males, times 14, choose 7 females. So there's picking 1 male, or sorry, picking 2 males, 1 male, 0 males, and then we'll divide that by the total ways we can pick everybody, which is 24. Choose our 7 people. That'll give us our probability that we don't want, and we'll subtract that from the total probability of 1, and that'll give us the final result, which works out to about 0.6430. So there's about a 64% chance that we will have 3 males attending. And then what is the expected value of male and female students chosen? Well, the expected value for males is equal to the number of dependent trials. So we're doing 7 people. In this case, we're pulling 7 people for the attending the workshop. We have a total of 10 males. We're going to divide that by the total of 24 people. So 7 times 10 divided by 24, that's going to get us 2.92. So we would expect 2.92 males to attend, and then our expected value for females is equal to the 7 people we're selecting times the 14 females that we can choose from, divided by the total of 24. And in that case, we're looking at 4.08. So we'd expect about 4.08 females, 2.92 males. If you tally those up, you're going to get 7, which those are the 2 options. We need females and males, so we expect that many males, then the remainder must be females. So that's where the 4.08 comes in as well. So these 2 should sum up to our total number of attendees. Okay. one more question here. We're looking at using information to solve within our equation for our expectation. So this is something that does happen when they're trying to determine, say, a total population. So here we have 500 foxes were caught and tagged last summer. 80 foxes were caught this summer, and 34 of them had tags. So we can use that to figure out an expected population or total population size, given that if we use our expected value equals the RA over N. And so if we fill this in with the information we have, catching 80 foxes, we would expect that 34 of them had tags. So this is our expected value, 34. Our number of foxes that we caught is 80. And so those are the number of, it should be the successful outcomes. So there was 80 successful outcomes out of 500. So there's 500 total outcomes, 80 successes, over the total population, which is what? We don't know. So that's our x. Let's use an x. So 34 equals 500 times 80. So our total number of outcomes of 500 foxes, 80 of them that were successful, and 34 being our expected value. So we just do some algebra here, and we can solve that. These two will end up flipping positions. You can do it step by step if you want. These would multiply to 40,000. It's going to be divided by 34. And then when we work that all out, the overall population that we would expect to find is 1,176. So we'd expect to find about that many foxes in total. So we catch some, we tag them, and then when we catch some again and tag them, we look at the proportion of the population that is tagged, and then we use that and extrapolate from what we had what we totally tagged to what we found the second time, and extrapolate that into the total population, in this case 1,176.